So now that we know that the limit of the right-hand sum and the limit of the left-hand sum are exactly the same thing, we can give a name to this. So we call the value that we get when we take the limit as n goes to infinity of the right-hand sum, which is the same as the value as n goes to infinity of the left-hand sum. We just proved that those are equal. We call this the definite integral. And as we said earlier, integrating means putting things together. So somehow we're putting all these little changes together, the little changes in the object's velocity, all the different changes in position, we're adding them all up to figure out how far the object traveled. Or we're adding up how much oil leaked out in each little interval to figure out the total amount of oil that leaked out. Or we're adding up the number of people who got a certain disease on a certain day, on each day. We're adding them all up to get the total number of people who got the disease. That's the idea of integrating. In fact, in the book War and Peace, Tolstoy goes into a very extended metaphor about the integral calculus, and we'll try to put a link to that in the website. So we call this the definite integral of y equals f of x on the interval from a to b, and we denote this with this new symbol here. And this symbol reminds us of what we are doing here. This is a fancy s. And this f of x d of x, this is sort of like when we took dy over dx. Remember that dy over dx, the derivative, is not an actual fraction. It's a great symbol because it looks like a fraction, and it reminds us of where we got the derivative by taking the limit of the change in y over the change in x. We're doing exactly the same thing now. We're also taking the limit as the width of each rectangle goes to 0. So that's just like what we were doing when h went to 0 before. This is one indivisible symbol. It reminds us of where this thing came from, the left that we were taking a value of a function times the width of the interval. Except now, when the width of the interval goes to 0 in the limit as n goes to infinity, just like in the derivative, we stopped writing delta y over delta x. Those were actual fractions, or that was an actual fraction. And we wrote dy over dx. Similarly here, we stop writing delta x and we write dx. And then the a tells us where we're going to start counting the area, and b tells us where we're going to stop counting the area. This symbol came from Leibniz way back in 1675. He was the one to introduce this fancy script s. And Fourier in 1822, not the same Fourier you may have met in your philosophy class, wrote the a and the b. He was the first one to write it that way. By the way, I hope that if you looked at that L'Hôpital's rule paper on the website, that you will have seen the great benefits of the improvement in notation that we have since then. Reading that paper is quite difficult. Now let's practice doing some of these definite integrals just so that we can get used to the notation here. So these aren't meant to be very exciting. The integral from 1 to 5 of 7. So all we can do now, the only way that we have to evaluate these integrals is by looking at a graph and computing an area. So here we're going from 1 to 5. And what does the graph of 7 look like? 7 is just a horizontal line at a height 7. So we're just going right along here at a height of 7. And we're computing this area. So we just get a rectangle, and the width of the rectangle is 4, and the height is 7. So the area here is just 7 times 4, which is 28. I think we've seen that number 28 before, haven't we? It's one of those perfect numbers, remember, from earlier in the semester? So this integral is 28. So there you go. We've computed our first definite integral. Remember when we had computed our first derivative? That was exciting. Here's our first definite integral. The area under the function 7 from 1 to 5 is 28. And again, the only reason we're able to do this is because we happen to have learned a formula in geometry class for the area of a rectangle. How about this one? 2x plus 6. Let's hope that geometry can help us here as well. So the graph of 2x plus 6 is a linear function with a y-intercept of 6 and a slope of 2. So we are looking for this area here, going over to 4. Now this shape is called a what? I think we call it a trapezoid. And there is some formula for the area of a trapezoid, but you might not remember it. I don't remember it. How could we figure this out without remembering the formula for the area of a trapezoid? We could break it up into a rectangle and a triangle. We could compute the area of the rectangle, compute the area of the triangle, add them together. So the area of the rectangle is what? It is 6 units tall, 4 units across. So that's 24 units. What's the area of the triangle? So the area of a triangle is 1/2 base times height, right? So 1/2. The base is 4. And what's the height of this triangle? Do you know what the height of this triangle is? We can figure out this y value here by plugging 4 into the function. So we get 2 times 4, 8 plus 6, that's 14. So the height of the triangle is what? We're going from 6 up to 14, so that should be 8 units. And another way to think about that is, what's the slope of this line? The slope of this line is 2. Every time I go over 1, I go up 2. So if we go over 4, we should go up 8. So we should go up from 6 to 14, which is 8 units. So that's 16. So therefore, the total area here is 24 plus 16, or 40. So the goal of these problems is to get us used to this notation, the new definite integral notation, and to point out in what situations we can actually compute them and in what situations it's a lot harder. So here we had just a rectangle, here we had a rectangle and a triangle, and so basic geometry saved the day for us. What about here? Sine of x. So the graph of sine of x from 0 to 2 pi looks like this, as we saw back in week 2. And we also discussed in week 2 whether these pieces are really semicircles. And I hope you remember that we decided that they were not semicircles. So what should this equal? There's a couple ways you can think about this. One, if this were a rate of change. So maybe this is the rate at which water is coming into a tank. So for the first pi units of time, the rate is positive, meaning above the x-axis. So what is happening to the amount of water? The amount of water is going up. For the next pi units, the rate of change is negative. So what's happening to the amount of water there? The amount of water is going down. And how does the amount that the water went up compare to the amount that it went down? They're exactly the same, because this curve is perfectly, this is an exact copy over here of what we have there. So what should the actual change in the amount of water be during this period of time from 0 to 2 pi? It should be 0, because the amount of water we gained is exactly the same as the amount of water that we lost. Or if this were the rate of change of a population, the gain in the population here is exactly balanced out by the loss in the population over here. And this goes back to the fact that we are thinking about signed area. We're thinking about this below the x-axis as counting as a negative. So we expect the answer to be 0, and the answer is 0. You can also do it purely from the definition of the left or the right-hand sum. Right? We were doing something like this, f of x sub k delta x. And anytime that I pick, remember, n is going to infinity. So essentially, you're using basically every single point along the curve. So if I've got a point here, whatever this x value is, that gives me some positive, you can see that there's going to be another x value here that has exactly the same y value except a negative. So if this were to say y equals positive 0.7, this is y equals negative 0.7, and therefore those rectangles in the sum are going to cancel each other out perfectly, and we're going to get 0. So all of these first three we're able to do using either geometry or, again, geometry basically here. Let's go back to that problem that we postponed, where we were doing the object that was moving at t squared meters per second. And we were trying to figure out how far it traveled during the time 0 to 2. So we had gotten an underestimate of 1.75 meters and an overestimate of 3.75 meters. And we had asked you to try to make a guess based on the applet what you think it should be. So certainly somewhere between 1.75 and 3.75. So now we have a way of doing this. We are trying to find the exact area under this curve from 0 to 2. Unfortunately, our geometry teachers never gave us a formula for that. People were able to figure this out before Newton and Leibniz, by the way. Archimedes used something called the method of exhaustion, where he would draw like a tangent line here that would give a triangle down here. Then he would draw another tangent line and another tangent line that would give 2 more triangles. And he knew how to find the areas of triangles, and he basically came up with a formula for adding up these infinitely many triangles that are all related to each other to compute the area under a parabola. He did that very successfully. But it's difficult to do, and now there are more modern ways using calculus to do it. Well, we have to go back to the limit definition of the integral now. So remember, earlier we used to go back to the limit definition of the derivative when we didn't know how to compute a derivative. Then we got all of our derivative shortcuts. We're doing the same thing here, coming up with a limit using the limit definition of the integral. So we're going to take the interval from 0 to 2, break it up into n pieces, each of which should be how wide? 2 minus 0 over n, or just 2 over n. So let's label these pieces here. So this first one is 2 over n, because I'm going from 0, I'm adding 2 over n to get to the next t or x value. Then we're going to add another 2 over n to get to here. So 2 over n plus 2 over n is 4 over n. Then I'm going to add another one, 6 over n. And we'll keep going until the very last one is 2. And 2 is the same as saying what? It's the same as saying 2n over n. And what I've drawn here is the right-hand sum. It doesn't matter whether we do the left or the right-hand sum. As we proved, as n goes to infinity, they're both equal. For various technical reasons, you can try the other one if you like. This ends up being slightly easier to do. So let's do it. Let's take the limit as n goes to infinity of the right-hand sum. So let's start with this first rectangle. Since it's the right-hand sum, when we have the choice between 0 and 2 over n, we choose the one on the right, which is 2 over n. So to figure out the height of that first rectangle, we do f of 2 over n, and we multiply by the width of the rectangle, which is always 2 over n. And you can go back and compare this to when we did n equals 4. If you look at when we did n equals 4, the first term in the right-hand sum was f of 1/2, which is the same as saying 2 over n, times 1/2, which is, again, is the same as saying 2 over n. So this agrees with what we did back then. Let's do the next one. We choose between 2 over n and 4 over n. We pick 4 over n. So the height of that second rectangle is f of 4 over n, and the width is still 2 over n. And then we just keep going. The next one would be 6 over n, 2 over n, all the way till the end here. F of 2n over n, 2 over n. So you can already see this is not nearly as easy as the previous 3 examples. So there's 2 reasons that we're doing this problem. One is because to show you that it actually is possible in some cases to do it. But also it's to motivate us to find a much easier way, and calculus will let us do that. Just as we don't use the limit definition of the derivative every time now. Let's figure this out. F of 2 over n. What is our function f? F of x is x squared here. F of t is t squared. So if I square 2 over n, we get 4 over n squared, still multiplied by this 2 over n. F of 4 over n means you take 4 over n and you square it. So that gives us 16 over n squared times 2 over n. And then 36 over n squared times 2 over n. When we square this, we get 4n squared over n squared times 2 over n. Each of these terms on its own is going to 0 as n goes to infinity. But you have infinitely many terms. So this is another one of these indeterminate forms. You're adding up infinitely many things that are each going to 0. So it's like an infinity times 0. We can factor out of this, though, right? What can we factor out of all of these terms? They all have an n cubed on the bottom, and they all have at least an 8 on the top. So I can factor out an 8 over n cubed. And what's left from the first term when I have factored that out is just a 1. And would you agree that if I felt like it, I could write 1 squared instead of 1? I think that's okay. If I factor, this is a 32. If I factor an 8 out of it, I'm left with a 4, which is the same as 2 squared. This is a 72. If I factor an 8 out of that, I'm left with a 9, which is a 3 squared. And if I factor an 8 out of the top of this, I'm left with an n squared. And again, we can see this is an indeterminate form. 8 over n cubed is going to 0, but the sum of this is going to infinity. And now this is where we need some magic. So there's no algebraic thing that's apparent what to do next. But luckily, there is actually a formula for adding up the sum of the first n squareds. If you know that formula, please say it now. So this very useful formula without which we would just be stuck and have to stop right now, is that the sum of the first n squares is equal to n times n plus 1 times 2n plus 1 all over 6. Now, we're not going to prove this formula in this class. This is not the place to prove it. A good way to prove it is using a method called proof by induction. There are various geometric ways to prove it as well. Let's just see if it at least works for some particular value. Let's check n equals 3. Now, of course, if it works for n equals 3, that proves nothing, but it just maybe helps us see that it does at least work. So if I do 1 squared plus 2 squared plus 3 squared, I think we get 14. And if I plug 3 into this, 3 plus 1, 2 times 3 plus 1, all over 6, that also gives me 14. So it works at least for n equals 3, and you'll just have to take my word for it that it in fact works for any value of n, and that it is possible to prove that. And this comes to our rescue, because now we can rewrite this as 8 over n cubed. And instead of writing this, which really, there was nothing I could do with that. There's nothing to do next unless we have this nice formula. Now I can write this, times n plus 1 times 2n plus 1 all over 6. And now this is something that is solvable using algebra. So this n can cancel with that cube there and give us an n squared. The 8 can become a 4 by canceling with the 3 and giving us a 6. So now what have we got? Limit as n goes to infinity. If I multiply out on the top, well, I'm going to put a 4/3 out front. How about that? 4/3, and then put the n's separately. So I've still got an n squared over here. And if I multiply this out, 2n times n gives me a 2n squared. In the middle, I get an n times 1 and a 2n times 1, which is a 3n, and then a plus 1 at the very end. And you might be saying, oh, let's use what? L'Hopital's rule. But the way this was done historically is people did not necessarily do this integration before differentiation. So we would like to do this without any previous knowledge about calculus. So strictly from algebra. And we can. So here we go. So the limit as n goes to infinity. We've got our 4/3 out front. And now we can simplify this. 2n squared over n squared is just what? That's just 2. 3n squared over n squared is 3 over n. And then we have a 1 over n squared at the end. And for example, if you now plug in n equals 4, you should get the same answer that we got for the right-hand sum before. Now, what happens as n goes to infinity? 4/3 doesn't change. 4/3 doesn't care about n. Neither does 2. But what happens to 3 over n as n goes to infinity? That goes to 0. What happens to 1 over n squared? That also goes to 0. So what's our answer? 4/3 times 2 equals 8/3. So if, based on the applet, you had guessed 8/3 or 2.666 repeating, you were right. That's how far the object traveled on this interval between time 0 and time 2. You'll notice that it's not halfway between your two estimates of 1.75 and 3.75. Halfway between those two would be 2.75, not 2.66666. Well, that problem might have scared you. So let me just tell you, we will never have to do a problem like this on an exam or a homework. So I'll write it on the board even though I don't really want to. So we'll never have an example like this on an exam or homework. Just like part D. The point of doing this, as I said before, was to show you that it can be done. So in this case, it was done. It wasn't easy. And if we hadn't had this formula come out of the blue to save the day, we would have been stuck at this point. So it was possible to do. It wasn't easy. And it motivates us to find another way to do this, which is what we'll come up with next. But one other thing that I'd like to mention is that it's not always true that you're going to get one of these helpful formulas to come out and save you. So it's true that there is a formula like this for the sum of the perfect cubes, the perfect to the fourth power, fifth power, sixth power, all of those. Those are all, we can all do of those. But if I were doing the function instead of t squared, 1 over t, we would get to here and we'd have something where we're adding up reciprocals, and there is no formula. And it's not just that we haven't figured it out yet. You can actually prove that there is no closed form formula for that, meaning you would get to this point and then you would be stuck. There'd be nowhere to go. Same thing for sine of t, cosine of t, natural log of t, e to the t, all of those functions. We get to this point and then there's nowhere to go next because we don't have one of these helpful formulas. And it's not that we haven't found the formula yet. There simply is no formula. We can prove that it doesn't exist. So we have a check your understanding now to help you make sure that you understand this new notation for the definite integral. And then we're going to come back and try to come up with a much faster way of finding these areas.